All right, this topic is fairly easy. It's just asking us to write a concentration equilibrium constant expression. So here is the reaction. Okay, it's in a homogeneous equilibrium. How do I know? Because the states, the reactant states of our reactants and products are exactly the same. They're all dissolved in solution. Okay, solvated by water molecules. That's aqueous solution. It says write the equilibrium constant expression for this reaction. So how do I write the equilibrium constant expression? Well, just like it says in the notes, if you consider this general reaction here, where you have reactant A, and the lowercase a represents its stoichiometric coefficient. So let's say I have two reactants, capital A and capital B, and their stoichiometric coefficients are the lowercase a and b. And I'm going to form two products, C and D. Well, one thing that we learned in this chapter is that the majority of reactions are actually reversible. I know up to now we've only talked about reactions going in one way, one direction, unidirectional. But in reality, majority of reactions are reversible. So that's what this double-sided arrow here is for the yield symbol. And so if I want to write the equilibrium constant expression for this reaction, A plus B yields C and D, with this being the stoichiometry, the stoichiometric coefficients there, it could be any number, then the equilibrium constant expression, so let's say this is measured in molar concentrations, Kc. Kc would be equal to the product of our product, so this times this, product means multiplied by, it'd be the product of the concentrations of our products, but raised to their stoichiometric coefficients. So that times that divided by the same thing for our reactants, also raised to their stoichiometric coefficients. This is the equilibrium constant expression. Now, these, let's say that we got these measurements here for how much of this we made, how much of this we made, or how much of this we have in concentration, then we'd be using Kc. But if this were done by measuring partial pressures, let's say that these were gases, it'd make much more sense to measure the amounts of gases as partial pressures. Of course, that's what our equipment would allow us to do. So in that case, we'd use Kp. This is still an equilibrium constant like this is, except this is indicating that we've measured the concentrations of our substances in the reaction as pressures instead of molar concentration. So it just depends on whether you have gases or not, or if you have a solution. Of course, if you have a solution, it makes more sense to measure with molar concentration. Okay, so we'd have the same thing here, except this would be the partial pressure of C raised to the stoichiometric coefficient times the partial pressure of D raised to its stoichiometric coefficient divided by the partial pressure of A raised to its stoichiometric coefficient times the partial pressure of B. Okay? So now let's answer this question finally. What are our products? We have this. This is our product, and we have two reactants. Okay? Also, I notice that these are in solution, so again, we are going to be looking at a Kc here. So Kc is equal to the concentration of our product, which is H2C2O4, raised to what power? Well, assuming this is balanced, the coefficient here is 1, so we could just leave it like that, divided by the concentration of our reactants. We've got hydronium raised to the second power times oxalate, C2O4, 2 minus, raised to what power? That's a 1, so it just stays a 1. Don't put this 2 minus out here. You're not going to raise it to the 2 minus power. Okay, this is just a polyatomic ion, okay, oxalate. Just like we put the plus sign inside of the brackets here. That's hydronium, H+. And so this is our equilibrium constant expression. And what it's telling us is that for this reaction, at a specific temperature, once this reaction reaches equilibrium, the ratio of our product raised to its stoichiometric coefficient divided by the concentrations of our reactants raised to their stoichiometric coefficients multiplied by each other is equal to this value. And this value, this Kc, will always be the same regardless of what our starting concentrations are when we first start this reaction. Okay, so that's why this is called a constant, because at a constant temperature, this remains constant regardless of our initial concentrations.